This is going to work, right? Just magically, boom! Very good. Let me see. Oh, but I need to connect this one as well. Technology. Nope. Go back. Good. Well, welcome everyone. Thank you for attending. I'm gonna try to entertain you for 30 minutes, telling you a little bit about how we are training vision language models, how, well, vision is not a solved problem at all, and there's some people that are still in the caves doing some research about it. My talk is called Redefining Small and Efficient Multimodal Models, and I'm gonna put my phone here to check the time. Good. You find me on socials as Andy Marafioti everywhere. My given name is Andrés, but my parents call me Andy, so don't feel bad about it. It's really okay. So, why multimodal models? So we know that LLMs are really good at text, and it makes sense that as we try to develop AI, that we would focus first on text, because we are social animals that interact with each other. We developed all of this language in order to give us messages, and it's just the way that we interact, right? So it makes sense we start with the sort of thing that we know, but in reality, text is a super limited environment for conversations and for experience in the world. And if we think about our brains, we have most of our brain capacity for vision, for trying to interpret the world visually. And that is just completely lost in these text models. Also a little bit, they should have speech, right? We should be able to talk to them, to try to accelerate, and to try to enrich a little bit the type of information that they can get from us. But that's still coming. Right now, because our text models are good enough, we're starting to add other modalities to them. Most state-of-the-art models are also able to see vision, or see images, see videos, and I'm going to tell you a little bit today about how that works, but also why we focus on trying to make them really small and really efficient. We've been at Hugging Face developing now vision models for 3 years, and we were looking at all open source models that get uploaded to our OpenVLM leaderboard, and we were noticing an interesting trend. So ever since we started tracking this back in 2023, models have been having a mean around 10 billion parameters, and they have been growing both towards larger sizes and towards lower sizes. So we see there are more and more. Oh, no, what did I do? Oh, magic. Okay. So we see there are more and more small models, but they sort of get stuck around 1 billion. And we wanted to try to accelerate this development, to try to give a push to the community, because at this size, it's still quite hard to iterate, it's still quite hard to do ablations, and we just wanted to facilitate that for people. So we started working in more small models. This is a little bit showing where we're headed. And something else that we noticed is these models, they seem small with 2 billion parameters, but actually they need a lot of RAM. So some of these 2 billion model parameters still need 40 gigabytes of GPU RAM to run, which is, well, if you have an H100, that's easy. But for most people at home, this is just unusable. So we wanted to try to see if we could address this problem. And the way we did this was with a very simple architecture. And this is not super new. I'm going to try to walk you through a little bit how we give vision abilities to a language model. There's the beautiful SmolVLM from Lubna and colleagues. And what we do to try to add vision to them is we start with an image, like this beautiful Hugging Face logo. And then, because we want to be efficient, we split it into a whole bunch of different parts. Each of these different parts goes to a vision encoder, and you can think of the vision encoder as a small network that tries to understand the image and outputs a bunch of features from this image. So the features are still more or less localized in a horizontal and vertical axis, but now instead of having just the one dimension, they have several. So they have several channels here. Then what we do is we have a process called pixel shuffle, which I'm going to tell you a little bit more about in just a second, to try to reduce the amount of tokens that go into the model and try to make them a little bit more efficient, use less RAM, a little bit faster. And then this is very crazy. I don't know if you were today at Luis's talk. Blew my mind. He was talking about the embeddings. Here we have a linear layer that goes from these encoded images to the input of the language model. So you can think this small linear layer, its job is to put the embeddings somewhere where all of the embeddings for the words are. And it's crazy that it works, but actually it does work. You then just pass the tokens to the model. You have a bunch of data with these tokens of vision and text that sort of relates to the vision, to the image, and kind of magically the language model learns. So this is a very simple architecture, very efficient. Now, how do we manage to make it not use 40 gigabytes of RAM? Well, one of the things that we do, for example, is this pixel shuffle that I was telling you. Just output of our vision encoder, we would have something like on the top left, 64 times 64 features with one channel. This is equivalent to 4,000 tokens. Now, from the transformers talks that you've heard today, you know that we need to then compute the attention between all of those tokens, one to the other, and all of them towards the text. So even if the model is very small and it doesn't have a lot of attention layers, you still need to do a lot of computations to get a lot of information in there and try to really understand what's going on. So what we do is we just reorder the data a little bit. We take every group, let's say, of 4 pixels, 2 by 2, and instead of leaving them like this, we put them into the channel dimension. So basically, going from this one to this one, what we do is we happen to have now 4 channels, which are just 4 pixels that were one next to each other here. Now they're just one. And you can see on the top of the face, there are 2 lines of pixels, 1, 2, and now there's only 1, because every 4 got together. And just doing that already reduces your amount of tokens to 1,000, which already gives you way more efficient models. You can do it again and go to 256, and you can do it again and go to 64 tokens. But what happens here? You can probably already tell that as you go further and further, you start to lose a lot of localization, a lot of information in the 2D space that's important. For us, we look at this, and it's like, yeah, I don't know what that is. It's like a something. Here, maybe you can tell that it's a Hugging Face logo, but you cannot really say much about it. Here, it looks quite good, and here, it's quite perfect. So as you do this more and more and more, you really start to lose a lot of information that might be relevant, and that's sort of what we see. So we did some ablations for this. Here on the bottom left, you see pixel shuffle 2 or 4. So maybe going back, that would be between this and this. We didn't even consider doing that just because we were aiming to go very high in efficiency. And we didn't get to do this because doing by 4 already sort of told us the story of where we're going. So here for 2 very small model sizes, 256 and 500M, we compared doing 2 and 4. And for the smallest model, it's basically the same. The smallest model doesn't really care. But for the medium size, the 500 million, it actually improved doing more pixel shuffle than doing less. Now, why could that be? My idea, and this is just an intuition, is that the 500 million model is not smart enough to really keep a context of so many tokens. So you give it 1,000 tokens of this image, and at some point it just loses track of what it's looking at and starts thinking about something else. And by the time you get to the output, it doesn't even remember what it was looking at. But when you go to a higher pixel shuffle, it actually keeps a little bit more track of the things, has a little bit more of an idea of what's going on, and at the end, it's able to output something relevant. We did some other experiments to try to optimize this model. We played with the context length. The context length I haven't really heard today in this stage being mentioned. It's how many tokens a transformer can see. So we optimize transformer networks to see an amount of tokens. It can be 2,000, 8,000, 16,000, or more. There are some with 1 million tokens or 10 million tokens. It starts to get pretty crazy when they measure it in Bibles. So you can pass 1,000 times the Bible. Like, okay, that's a use case for someone else. But yeah, here we see that as we increase the context length, we manage to get better performance out of our tasks on the top right. And why didn't we go further than 16,000? Well, what we start to see with these small models is, as I said before, they just lose track. You try to pass more and more tokens, and they start to not really follow it anymore and just decrease in performance. But up to 16,000, it was good. We also did a little bit of an exploration in where do we put the model parameters? Do we get a larger vision encoder, or do we get a larger language model? So here in blue on the top left, you have a small encoder, vision encoder, or a larger one with 400 million parameters. What we can see for the, let's say, the smallest sizes here is that for this language model combined with this vision encoder, having the larger vision encoder actually made the results worse. And for a medium-sized language model, having the larger vision encoder improved quite a bit the performance. But in this case, what we see is you get a 67% increase in amount of parameters, and you get just like a 10% increase in performance. So because we were really focused on efficiency, we chose for the two small models to go with the smallest vision encoder, and for the larger one, because then the difference between the two vision encoders is only like 5% of parameters, then we go with the larger one. Our models are also equipped with with video capabilities, so they can view videos and describe them and say what's going on, do a lot of tasks with videos. And we explore doing frame averaging. So if you have a video, a little YouTube clip, just average every 8 frames or every 4 frames and just pass 1. And interestingly, these always decrease the performance for small models. We were quite puzzled because for pixel shuffle, as I told you before, you're basically averaging a lot of information, and that's really good for the model. But if you average the information across time, it actually decreases in performance. So that was something interesting. Oh yeah, and we have some training tricks. I'm showing you a little bit of the secret sauce. I hope I still have you here. So these are a few small things that we tweak during training, and we actually get better performance with each of them. The blue one on the left, well, we have two plots, right? On the left is just image benchmarks, on the right is video benchmarks. The blue is just the baseline. We pass some data and we train on it. The red is passing a system prompt to our models, where we tell the model something like, you are a very capable vision model that's going to solve this task amazingly. And the thing does better. Isn't that crazy? Like, really, it's just a few motivational strings before it starts the task, and it really gets ramped up. Then on green, we pass a little intro and outro string. So we tell it, right now you're going to watch a video. Then we pass all of the video tokens, which are like the image tokens that I told you before, just several after the other. And then we tell it, you just saw a video. And then the question. And that also really helps. The model, like I said, sort of loses track maybe at some point if you pass a lot of data. And I guess it's good to tell it, like, hey, this was a video. And it's like, ah, yeah, right. Sure. And the last one is also a little bit of a training trick, which is we don't train on the user prompt. So if we have a data set with a lot of questions about YouTube videos, for example, the questions are not very rich. We might have 1 million videos and maybe, with luck, 10,000 questions. So they get repeated a lot. What's interesting are actually the answers. So we mask all of the questions for the model. We don't train on those. We only train on the answers. And you can see that here, it hurts some of the benchmarks, but it actually increases the average. So it makes the model a little bit more robust. So we went with it. And with these few decisions, basically trying to see, okay, how do we make a model? Let me check the time. Gonna pace. Trying to see how do we make the model very efficient? How do we train it very precisely? What sort of things we can do? We went into benchmarks, and there we compare a little bit against other models. But here we really try to break a little bit the mold. Usually when you compare models, people compare them on model size. So 1B, 2B, 8B. And for LLMs, that makes a lot of sense, because the model size is very correlated to the amount of compute that you're going to need to use the model. But for VLMs, that is not the case. I showed you this iceberg slide where small VLMs require a lot of RAM. And we decided to just compare them on RAM use. And we saw like there are some models like MoMoE, it's a mixture of expert, and you need 28 gigabytes of RAM to run it, and they say it's a 1B model. We have Qwen 2BL, it's also a great model, 2B, it needs like 15 gigabytes of RAM. Our largest model is also 2B, and it only needs like 5 gigabytes of RAM. And our smallest one, it's 256 million parameters, and it runs with less than 1 gigabyte of RAM. So we were really focusing on trying to make them very small and very efficient. We sort of achieved that, and we also achieved a model size that before was completely unexplored, which was, well, 256 and 500 million. You saw at the beginning where I was showing you all of the models, the smallest were 1B, so either half or 1/4. And interestingly enough, here on the bottom right, we have a model that we released I think like 18 months before the 256 million, and it was an 80B model, so quite big, quite chunky boy, and it was state of the art at the time. And now we went for a model that's 300 times smaller, and it still performs better. So that's just, to me, indicative of the speed of development. And when people start to play with these small models and maybe say, oh yeah, they're not as smart as the large ones, you're comparing against the large ones from today, which are better, of course, that's, thank God. But if you think about the speed of development of, okay, in 1.5 years, these tiny models are better than the ones that were huge before, then you can try to think a little bit forward and see basically the same. So I'm very bullish on small models. I think I had hidden this one. I'm showing it again. I just want to show a little bit the RAM usage here on the bottom for the 3 model sizes. Did I? Yeah. For the 3 model sizes at batch size 1 and batch size 64. For the smallest one is under 1 gigabyte. For 500 million is 1.2. And at batch size 64, you get 15 gigabytes and 16 gigabytes. So you would think, if the 500 million is so much better in the benchmarks, why don't you just use the 500 million? And I'm going to justify it to you why we went and still built a tiny one. And yeah, these are a bunch of benchmarks: single image, multitask, video. On video, we beat some models that were 7B and state of the art. And in single image and multitask, we are still performing really well in comparison to state of the art models. Oh, and I think Luna told you a little bit about this. We developed an app that we deployed to the Apple Store. You can get it on your iPhone. I think it works like with iPhone 14 Plus or something. The video is a little bit speed up, and the model is very small, not great. But you can basically point your phone at stuff and ask it to describe. We got very good feedback from vision-impaired communities that asked us first to add an audio way to talk to the model, to try to tell it to describe stuff, or etc. And they told us that they were using it and they are finding it useful. So it's cool. And we also open sourced all of the code in case you want to develop your own apps that run on an iPhone and they can do this sort of thing. So yeah. That was nice. Here are a few frames. Did I wanted to say something else about this? check important info for mistakes. Yeah. So yeah, a little bit like our goal at Hugging Face is not so much like selling you models, but it's a little bit opening doors for the community to develop things. So when we do things like this, we don't want to create an app for you to go and use it and be super happy with it. It's more like showing you, hey, you can build these things, you know? You have now a tiny model, you can fine-tune it, you can deploy in iPhone apps, and you don't even need a cloud. They can run on the phone. It works. And yeah, that's a little bit important for us, like showing what things are possible. But besides it running on a phone, we wanted to see a few. I still have like 10 minutes, right?
Oh yeah, plenty of time.
Good. Good. So besides deploying this to a phone, we wanted to see other real-life use cases. One thing that we did for that. Oh no, actually, before it's this slide. Good. Okay, speeds. NVIDIA i100, that's a pretty big GPU from, guess who? NVIDIA. And you can see the tokens per second, how they grow with the batch size. And you can see for the largest model, you can increase the batch size and it fits, but tokens per second is pretty much the same. Basically, the card doesn't have enough RAM to parallelize everything. But you see for the smaller models, it actually grows. And for the 256 million model, from batch size 16 to 64, it still doubles the throughput that it has. Whereas the 500 million model doesn't. So what is the use case for the 256 million parameter model? Basically, if you're trying to process a lot of data and you can make this model work, which I'm going to show you in a second how, you can do twice as many documents or data with the same compute budget, which is quite important. Even though when you see like the amount of RAM that they consume is not that different. And on the right, what we did is we made a little web GPU application where you could enter with your laptop and the application would download the models and run them directly on your browser and do some benchmarks and give us back the benchmarks. And we put it on Twitter and we asked people to do it. And we got a bunch of results from people with Macs doing the benchmark. And something that to me is really interesting, we have a really powerful computer from 4 years ago that can still run these models, even the 2B1, on the web browser quite efficiently. And we see how newer machines, they are achieving very good throughputs on your browser. So for me, this is something that's really coming. And for people developing websites, it's a little bit of a wake-up call. Hey, you can just deploy a model on the browser. Any user that comes is going to be able to use it, and you don't need to host it even. It's just poof. So yeah, little view into the future. Now, we wanted to create these generalist models, but we actually want them for people fine-tuning. We want people having very cool use cases for them. We wanted to see if we could already partner with a few groups and see if they could develop cool stuff for the model before we even released it, because if it doesn't really work, then it's a little bit sad. The first people that we partnered with were a group from IBM who developed a library called Dockling. Dockling is a library to insert PDFs, and you extract basically the whole document parsed. So if you have a lot of PDFs or images of documents, you can basically scan them with this library, and then you can go through the data and try to analyze it. So they were thinking about something that they wanted to call SmolVLM, which was basically a vision language model that would take as an input the whole document and would produce as an output this weird text that they created. The way the Dockling library does it now, right now, is they have a whole bunch of models. They pipe them, they do stuff, and it works really well, but it's quite complex and it requires quite large models. So they wanted to see if they could make it work with the 256 million parameter model, because they have this exact use case of they have big GPUs and they want to process a lot of data very fast. It's IBM, so I guess their use case is that. And we train a model with them based on the 256 million model. This is processing an original document. It's a PDF image of, I don't think a blogspot, I think that we wrote. And it outputs this weird text that to us makes no sense. But then you can recover a docling document. Basically, the library sees that text and generates the document for you. And that weird thing would also be parsable by databases, by LLMs. So you can basically then do RAG on it very simply. You can search for stuff. You can do a lot of things that you wouldn't be able to do with the images. And it worked really well. Here in this example, it's a little bit cherry-picked because it's perfect. And that's a little bit what we want out of these models, right? Now, this is a tiny model, 256 million parameters in total. The LLM is 135 million parameters. This is like rough territory. But how does it compare to other models out there? So we compared it against Qwen 2.5 VL, which is a 7B model. That's 4 times 7, 28? 28, right? Yeah. To 28 times larger model, not specific for this task, but they can do the task. They target it. They say in all of their model cards and stuff that this is a task that they do, and they are considerably worse than our tiny specialized model. Now, comparing against other small specialized models, we're also way better. So clearly, this is a use case that sort of works. For the full page, we have an F1 score of 0.8. That sort of means that we miss quite a bit of things, and we add quite a bit of things. So we are far from perfect, but this was also our first go at the problem. So we collaborated with them. We did several experiments, wrote a paper about it, and we got quite far. My intuition is that in 1 year, maybe, this is going to be completely solved, because we are just getting more data, and because IBM, now that this worked, they are going to put a little bit more effort. And to me, it's an amazing use case for these very tiny models, a very specialized use case that just works great, and you save a ton of compute, you save a ton of money. And yeah, the good thing of collaborating with them as well was that it's open source from their side, so they release the model, the weights, and a lot of information. We're going to release the data. So that was a nice collaboration. Then we had a different one where we used this small model to build a database, basically. So imagine you have a whole bunch of papers, and you want to search through your papers and try to understand, I don't know, I want to know more about genomics. That's a word, yeah, genomics. So I type into the thing, hey, can you put me the most relevant papers on genomics from the last 2 years? That's my user query here. That goes to a retriever model based on ours that has previously indexed our whole database of papers, and it runs a query against this indexed knowledge base to get the most similar documents. So basically, from these maybe 50,000 documents, we can retrieve 5 if we want that are most relevant given on the query. And then we can pass those 5 documents to another model as context. We can tell the model, hey, the user wants to know about genomics, and these are 5 papers that are super relevant for him. Tell him about this information. And here you can use SmolVLM for the reader, but you could also use a large VLM, and you would still save a lot of compute by having indexed this database with the small model and by doing the RAG basically with the small model. How did this compare to other solutions that we had? Well, our 2B model is basically on par here with other 2, 3B models. But here we put the x-axis as parameters. And as you know, the Qwen model used 3 times as much RAM as us. So this is still true for this use case. It's still way more expensive, and it still scales a lot with batch size. So we are still very efficient, and we have the same performance. And we even have a very fair performance with the two smaller models. So there you lose like 5% from 2B to 500, and maybe another 5% from 500 to 256 million. But depending on your application, maybe which documents you retrieve, if you got exactly the best ones or not, might not be so relevant. So we were fairly happy with this result as well. And a little bit what's lying in the future for us. So Hugging Face just bought a robotics startup, a humanoid robotics startup, with this little Richie model. It can move around, it can grab stuff, and we want to try to open source a little bit more the whole humanoid robotics side of things. And for these models, it's clearly very important to have small visual language models that you can just tell, hey, can you clean my kitchen? And then they go and they do it. Wouldn't that be great? That's literally the only use case I'm interested in. So yeah, and with that, I hope I good on time. Awesome. With that, I pass it on to you. Please, Bill. Yeah, let's do a clap. And